Assalamualaikum and good day to all. This is the second part of the lecture for chapter 1. So in previous lecture, you have learned about the importance of chemical reaction engineering knowledge and relate it with your daily life. And also you now should be able to give a definition of reaction rate using your own words. And lastly, you should already know and understand different types of basic reactors and their application. For this lecture, we will focus on designing general mole balance equation in relation to the reactor design. To perform a mole balance on a system, you need a system volume. So this is the system volume. Any reactor with a volume V, that is a system volume. Now let's perform a mole balance on species A in the reactor. The mole balance on species A at any time t can be written as in minus out plus the generation inside the reactor equals to the accumulation. So in the flow system, it can be written as FA naught, which is the initial molar flow rate, minus the final molar flow rate, anything going out from the system, plus the generation inside the system equals to the accumulation of the species A in the system. So general mole balance equation can be written as anything that comes in minus anything that goes out plus any generation inside the system equals to the accumulation in the system. So for species A, you will have this general mole balance equation. So the generation GA equals to RAV. This is only valid if all system variables is constant. For example, the temperature, the concentration, the catalytic activity are all constant. Means that it is a small volume where everything have same value. However, the bad news is reactor system is rarely small, such that you can consider all the system variable are uniform. So how do we deal with the non-uniformity? Okay, let's say you have this system volume. So you have V1 and V2. Okay, the generation GA for system volume 1 equals to this equation 1. And for volume 2, for system volume 2 will be GA 2 equals to RA 2 times delta V2. So the summation, the total generation GA will be summation of number of the system equals to summation RA I, where I could be any number 1 and above, times delta VI. Okay, so taking limit m approaching infinity and delta v approaching 0, GA will be equals to RA dV. So when the number of small system volume is increasing, reaching the infinity, the change in volume will be very small that we can consider that the change is approaching 0. So the general mole balance equation can be written as FA naught minus FA plus the generation RA dV equals to dNA over dt. So this is the general mole balance equation for reactor system. Okay, so now we are going to modify the general mole balance equation to suit the reactor type. Okay, we look at the first reactor, batch reactor. So for batch reactor, we don't have any flow in and flow out. So FA naught equals to 0, FA also equals to 0. So the reaction is perfectly mixed, no variation in the reaction rate throughout the reactor. So you will have RA times V equals to dNA over dt. So for batch system, usually we are looking for the time required to achieve certain conversion, where the number of mole of A changes from initial amount from NA naught, it change to NA. So if given you the number of the profile, so the number of mole of A drops by time. So you need to know what is the time when the number of mole of the species A have reduced. So you have dNA over dt equals to RA times V. Rearrange the equation, you will have dt equals to dNA over RA times V. So taking the limit at t equals to 0 and A equals to the initial, and when t equals to t1, your NA will be equals to NA1. So T1 equals to the integration of NA1 to NA0 dNA over minus RAV. So this equation will allow you to calculate the time required to reduce number of moles of A from NA naught to NA at the required time. Okay, now we look at how to design mole balance equation for CSTR. Okay, so this is the general mole balance equation. Okay, first, since the main assumption is perfectly mixed, meaning that there is no variation in the reaction rate, so the term generation RA dV will be equals to RA times the volume. And secondly, since CSTR is operated at the steady state, means that the condition in the reactor doesn't change with time. So dNA over dt means the accumulation is equals to 0. So the final mole balance equation will be FA naught minus FA plus RAV will be equals to 0. So you can rearrange the equation to calculate the volume. We'll have V equals to FA naught minus FA divided by minus RA. So this will be the equation that you need to use to calculate the volume of CSTR required to reduce the flow rate of species A from FA naught to FA. Okay, so we have done the mole balance, the design equation for batch and CSTR. Now we continue for PFR. Okay, so PFR also known as a tubular reactors. So this type of reactors are mostly used for gas phase reaction. Okay, so the reactants are continually consumed as they flow down the reactor. So as they flow down the reactor, the reactant is consumed. Okay, so to design the equation, the main assumption is that the velocity of the fluid is uniform. So meaning that there is no radial variation of the reaction rate. It is only axial variation. Okay, so since the reaction rate will vary in axial direction, we will divide the PFR into smaller section. Okay, so we divide this PFR into very small section so that the delta V of the reactor is very small, that there is no special variation of the reaction rate within this specific volume. Okay, so delta, so generation GA will be equals to RA times the delta V. Okay, so looking back at the reaction, the general mole balance equation, so you will have FA naught, minus FA plus RA times delta V equals to 0 because there is no accumulation. This is a steady state operation. Okay, so you divide this equation with delta V, you will have FA naught minus FA over delta V equals to minus RA. Okay, so taking the limit as delta V approaching 0, the differential form of steady state mole balance on PFR will be RA equals to dFA over dV. So to find the volume necessary to reduce FA naught to FA, we have dV. Rearrange this equation. So rearrange this equation. So we have dV equals to dFA over RA. So V will be equals to dFA over RA. Okay, so this will be the equation required to calculate the volume of PFR. Okay, now we look at the last reactor type, packed bed reactor, PBR. Okay, so PBR is similar to PFR. The only main difference is that packed bed reactor involves the heterogeneous system, fluid and solid reaction, and also this reaction takes place on the surface of the catalyst. So the reaction rate is based on the mass of the catalyst rather than the volume. So the reaction rate is denoted as prime for heterogeneous system, and W is the catalyst weight required to reduce the entering molar flow rate from FA0 to FA. So instead of using V for this for packed bed reactor, we have dFA over dW equals to RA primes. So weight of the catalyst will be W equals to the integration from FA0 to FA dFA over RA. Don't forget the prime. So this is the equation required for you to calculate the amount of catalyst required in the packed bed reactor. Okay, so in this chapter you have learned about 4 basic reactor types and how to design mole balance equation from general equation to the specific reactor types. And also for each reactor, main assumption was made. So for batch and CSCR, it is assumed perfect mixing with no special variation. And for all flow reactors, we assume it is steady state. So this is the main assumption that you need to remember. Okay, look at this equation. This question. Okay, so this reaction is actually the reaction of A producing B, and is to be carried out isothermally in a CSTR. So in a reactor, in a flow reactor. So in a flow reactor, so your task is to calculate the reactor volume required for both PFR and CSTR. So given to you that the volume necessary to reduce 99% of A, meaning that your CA will be equals to 0.01 CA0. So the entering molar flow rate FA0 equals to 5 mole per hour. So you are given A minus RA equals to K, where K equals to 0.05 mole per hour dot dm cube. B minus RA equals to KCA, where K equals to 0.0001 per second, and C minus RA equals to KCA squared with K equals to 3 dm cube per mole dot hour. So the entering volumetric flow rate is given to you 10 dm cube per hour. Okay, you try this question when we will discuss in the class. Also, another question, look at this question and find out what is wrong with this solution. So your task is only to check what is actually the mistake in this solution. Okay, so we have come to the end of the first chapter 1. So at this point you should be able to define general mole balance equation in relation to the reactor design. Okay, I hope you try the two equation and we will discuss in the class. Thank you.